On -4, 1, find the intervals when the function is increasing and decreasing, concave up, concave down, find the all local absolute mins and maxes, find all points of inflection. So what we have here is a first derivative problem, and that's going to be for increasing and decreasing and for the local mins and maxes. Then we have an extreme value theorem problem, and that's when we're going to find the absolute mins and maxes. And then we have a second derivative question, which is concave up, concave down, and also points of inflection. So that is the second derivative test. So let's get started with our first derivative test. So we've got an f prime of x is equal to, so I'm going to call this my first and then this my second. So the derivative of the first is 6x times the second, which is just e to the x, plus the derivative of the second, which is just simply e to the x, times a 3x squared. Okay, first derivative test says set that equal to 0, but what's useful first is going to be to pull out a common term, and what I see is a 3x and an e to the x. Okay, so that's going to give us a 2 plus x. Okay, and if you want, you could rearrange that 2 plus x, if it bothers you, to be an x plus 2. I'm going to set this equal to 0 to find my critical points. So when will this be equal to 0? Well, 3 times 0 times e to the 0 will be 3 times 0 times 1. So if x is equal to 0, due to this one right here, that whole thing will be 0. And then here we have an x equals -2. So these are our critical points. Okay? Okay, let's continue with our first derivative test, and let's create the following. Well, remember we're on this interval -4 to 1, and I'm going to have to put the -2 and then the 0. Make sure it's in order from least to greatest. So this is my first derivative test, so I'm going to choose x equals, let's say, -3 here, x equals -1, and an x equals 0.5. We're plugging those values into our first derivative to see what sign they are. So let me do that. Okay, when I plug in -3 into the first derivative, I get a 0.448, which is a positive. If I plug in -1 into the first derivative, I get a negative. And then if I plug 0.5 into the first derivative, I get 6.18, which is a positive. All right, so let's deal with our increasing and decreasing first. So remember, this is going to be increasing here, then decreasing here, and then increasing. So let's do with that problem. The increasing intervals are going to be from -4 to -2, union 0 to 1. The decreasing interval is just when the first derivative is negative, which would be right here, from -2 to 0. Okay, so we're good to go on that. But now we need to find the local mins and the local maxes. So remember, the local mins are going to be right here. Oopsie, I hate that. Local min is right here when it goes from decreasing to increasing, so that's going to be at 0, comma. The local max, so this is going to be a local min. The local max happens right here at -2 something. We also have a local min right here. See that on the endpoint? So -4, that's going to be a local min. And oopsie, that -2 was a local max. See that right here, local max. And then at our endpoint of 1, it also looks like we have a local max. Now, how do I go ahead and find these y values? Well, I'm going to take these x values and I'm going to plug them into the original function right here. So let me get those answers. And that's it. Basically what I've done is I've looked at my first derivative chart over here to find my local mins and maxes based off of our first derivative and whether it's increasing or decreasing. Do not forget to include your end intervals here, the endpoints. All right, so that's done. We're done with our first derivative test. So now we're going to go to our extreme value theorem, which is really quick. We know with the extreme value theorem to find the absolute mins and maxes, it either happens at a critical point or at an endpoint, and we've already located all of those. So all we have to do is look at this list of 4 right here and find our absolute highest. In this case, right here, this is going to be our absolute max. And the reason why is that 8 is bigger than all other numbers. Our absolute min is actually going to be this point right here. So this is our absolute. And that's because that 0 is smaller than both of those two numbers right there. All right, so we're done with both the first derivative test and the extreme value theorem. Now let's go ahead and talk about the second derivative test. All right, next we need to talk about the second derivative test. That's going to help us with our concavity and points of inflection. So we take our answer to the first derivative and we take the derivative again. Okay, so the derivative of this is going to be a product rule where I have to break it up into this. So the derivative of the first is 6 times the second plus the derivative of the second times the first. Okay, now let's go ahead and do that product rule with this. So now we have the derivative of the first is e to the x times the second plus the derivative of the second, which is 6x times the first. All right, what can we pull out? Well, it looks like to me we can pull out an e to the x. And it's possibly more, but let me just see what we get when we pull out e to the x. Well, we get a 6 plus 6x plus 3x squared plus 6x. So we can go ahead and just simplify here. And I get a 3x squared plus a 12x plus a 6. Right, 6x and 6x is 12x, 3 is 3. It looks like I can also pull out a 3. So I'll have f double prime of x is equal to 3 e to the x, and then I'll have an x squared plus 4x plus 2. All right, now we need to set this equal to 0. Are there any x values that would make this equal to 0? Nope. How about here? Yes, there are. There are 3 ways to figure out the x values that would make this 0. Your 3 options are number 1 to factor, number 2 to do quadratic formula, number 3 would be to use your graphing calculator. You would graph it, and then you would go to second calc and you would click on zeros and find your zeros. Unfortunately, this problem is not factorable, right? You cannot think of anything that adds to 4 and multiplies to 2. So we're either going to have to use our graphing calculator or quadratic formula. So what I'm going to do is I'm actually going to use the quadratic formula, and I can review in class how to use the graphing calculator if you prefer. But here our a is 1, our b is 4, and our c is 2. So the quadratic formula is a negative b plus or minus the square root of a b squared minus 4ac all over 2a. So the opposite of b, well, if our b is 4, we're going to have a negative 4 plus or minus the square root of b squared minus 4 times a times c all over 2 times a. I'm just literally plugging the variables in. Okay, next I'm going to do everything that I see under the square root, but I'm not going to take the square root yet. So in my calculator right now, I'm doing 4 squared minus 4 times 1 times 2, and I get 8 all over 2. All right, so what is this going to be? This is going to be 2 answers. I'm going to get a negative 4 plus the square root of 8 divided by 2, and then I'm going to have negative 4 minus the square root of 8 divided by 2. Make sure, ladies and gentlemen, you put parentheses, or else your calculator is going to get confused. Let's get those answers. Okay, I get a negative 0.586 and a negative 3.41. So we need to now draw, those are possible points of inflection. We need to graph on our chart our second derivative test. All right, so here's my second derivative test chart. Notice that I put my end intervals right here. Those are my endpoints from here. And then also when I solved using quadratic formula, I got this value and this value. And then I just chose x values that were in between these ranges. So now I need to take that x value, which is in between that value of negative 4 and negative 3.41, and I plug it into the second derivative. Remember, the second derivative is this, and we're plugging that x in everywhere we see an x. And when we do that, I get double prime of x is equal to a 0.022, which is positive. Okay, when I plug in a negative 2, I actually get a negative. I get f double prime of x is equal to a negative 0.812. And when I plug in 0, I get a positive 6. F double prime of x is 6. So I get a positive. All right, so answering the questions of concavity, here I have concave up because of the plus, and then I have concave down, and then I have concave up. So let's fill this in. Let's start with concavity. So we've got concave up right here. So that would be from negative 4 to negative 3.41. But then we also have concave up right here. So we're going to have a union, negative 0.586 to 1. Okay, we're using these values as our x's. These are intervals, they're not coordinates. We are concave down just from here to here, or negative 3.41 to negative 0.586. Okay, now we have 2 points of inflection. One is right here, because we go from concave up to concave down. And then here's another coordinate right here. Negative 0.586, we're going from concave down to concave up. So we actually have 2 points of inflection. Okay, the first being at a negative 3.41, and the second one being at a negative 0.586. Now, how do I get my second coordinate? Well, this is a coordinate, so we're always going to plug that into the original function right there, where we're going to plug in for x and x. So let's do that. Okay, plugging in, I got a 1.15 when I plugged in this x value into the original, and then I got a 0.573 when I plugged in that value into the original. So we are now done with the second derivative test. That gives us our concavity, intervals, and our points of inflection. That's it. Thanks for watching.